class we saw LP spaces, right? So earlier we had seen L1 space and its completeness. Then I defined the general LP space. So there is one idea which is to remember, which is that we move to equivalence classes to strictly get a norm. Otherwise, you don't get a. Otherwise it's a pseudo norm. If you stay with measurable functions, even with the integration condition that it should be finite, then you don't get. You have to move to equivalence classes. That was there in L1 also. But then we define general LP spaces, including p equal to infinity, and then there is a norm on it. It was not obvious that was a norm, so that was Minkowski's inequality that I showed. That so this Minkowski inequality, where is it? Minkowski's inequality. If f and g are non-negative measurable functions, then for p between 1 and infinity, this is 2. This inequality holds. It's very obvious when p is 1, 2, or infinity. Actually, when p is, especially when p is 1 to infinity, particularly p is 1 and p is infinity are very easy. But when p is infinity, you don't write this expression, by the way. When p is infinity, this entire thing has to be replaced by the essential supremum of f. But then it is also obvious. But for general P, it's not obvious. And last time we showed this, the way we showed it was to first prove another very important inequality called Hölder's inequality, which says that if f and g are non-negative measurable, then and f is p integrable with to the power p, and g is integrable to the power q, where p and q bear this relationship, then fg integral is bounded by normal this f to the p d mu 1 over p and g, which is easy to remember this way. If f and g are integrable, then L1 norm of fg is bounded by LP norm of f times LQ norm of g. P and q have to bear this relationship with each other. Okay. So there's I mentioned that this P and Q relationship 1 by P plus 1 by Q is 1 is actually something that is quite deep and it goes far. As I indicated last time in another, in response to some other question, much of this does not require infinite dimensionality. I mean, we can even see these things in finite dimension. So let me just indicate to you what is this LP-LQ relationship. I am not sure if you have done it or not in basic class, linear algebra class. So it's okay. We can do it now. Okay, so let's just so what is this PQ relationship, the duality relationship? In finite dimensional setting, I'll just because if you understand that, then you get the point. Of course, the proofs are not the same. We will have to prove it separately. Whether we will do it in this course or not, I am not yet decided. But let's talk about this. So, if X is a finite dimensional vector, if X is finite set, let's say call it 1, 2 up to n. And what is the measure I take? I take the measure which is the f is the power set and mu is counting measure on X. That means mu of any set is the cardinality of that set. Okay, so the cardinality of that set. So it is. So then, what is LP? In this case, LP is identified as Rn with the, let's say, equivalent to Rn with the norm so if X is a vector in Rn, norm xp is 1 over mod xi to the power p whole raised to the power 1 over p. Okay. So remember, I don't have to say this again. So if f is a function on function on x, basically that tells you what is f of 1, f of 2, f of n. So each of that is a real number. So we can write a function as a vector in Rn. So that is what I am writing as x. Okay. So x is a function. I mean, it's x1, x2, xn. x1 is the value of the function at 1. x2 is the value of the function at 2. xn is that's the identification between these two. But then what is the norm here correspond to there? The norm here is integral of f to the power p d mu, but mu is just uniform measure. So it just becomes this one. Summation mod xi to the power p whole raised to the power 1 over p. Okay. So this is what it is. So now in finite dimensional vector spaces, you have seen what is the dual. What is the definition of dual space of a vector space? Let's say finite dimensional vector space over R. What is the definition of dual space? Have you seen it? You have definitely seen it, but what is this? Yeah. So I could not hear.
The set of linear functionals.
The set of linear functionals on this space, right? Was the set of linear functionals, meaning they are linear maps from the vector space. So these are L is a linear map from X to R, having the linearity property. That's what linear functional is. Okay, so into R, that is the point. If it is general into some other vector space, we will say linear operator or linear transformation. But if it is into the scalar field, we will say that it's linear functional. So let us set of linear functionals on X. And what is that isomorphic to? What are the linear functionals on if X is Rn? In the case when X is Rn, see, the linear functionals don't depend on the norm at all, right? Whether something, if L from X to R is linear, that is just means that L of x1 plus x2 is Lx1 plus, I mean, L of x plus y is L of x plus L of y, and L of alpha x is alpha L of x. That doesn't have anything to do with the norm given on X. So this answer doesn't depend on that. So when X is Rn, what is the dual space?
Again Rn, right?
It is again Rn. But you have to say what is the identification. Is Rn.
The identification is essentially the any functional can be identified as something of the form a dot x, where x is your input and a is a vector in Rn.
Exactly. Exactly. So with the y and Rn identified with Ly in X star defined as Ly of x is summation. So these are linear, clearly. Summation xi yi is a linear functional in X, right? If you take x two vectors here, x1 and x2, then you will get the sum of those two and such things. So that is clear that these are linear, and these are all the linear functionals on Rn, that we know. Okay, so that part is okay. But what about the norm? Okay, so in general, but x star is not simply a dual. When X has a norm, one can define the dual norm, or one defines the dual norm on X star as, so if I have a linear functional, so let's call it L. I'll write star to indicate that this is the dual. So how is that defined? How do you define the norm on the dual? So the L is a function from X into R. So how do you define its norm? So have you seen this by any chance? So I'm just asking this to know if you have seen this or not. If you haven't seen, I'll be explaining anyway. So, but is this something you have seen? How would you define if X, suppose now X has a norm? How do you define the norm on the dual space?
I suppose you could take the operator norm on L.
Yeah, exactly. So what is operator norm? So it is,
Supremum over your unit sphere.
so you take supremum, but if you take supremum over the whole space, you'll get infinity. So you take supremum over the unit ball of X. And unit ball is defined in terms of the norm, right? So sup of Lx, absolute value, over norm X equal to 1, right? You can also write this as in many other ways. It is the supremum of Lx when norm X less than equal to 1, because taking it smaller will not help at all. It is also another way to write it is supremum of Lx over norm X over all X in X, X not equal to 0, because then you can't divide. So that is the one case we don't take, but this has many other ways of being defined. So this is the dual norm. Now question is when Rn comes with, so this we already identified this. So let's write that here. So when X is Rn with norm given as the norm P. What is the dual norm on X star, which is also identified as Rn? So what is the dual norm on that? That is the question. Okay, what is the, so it's the same question. We have already identified the space, but what is the norm? So it's just a matter of finding this maximum, right? So it is, so let's do this problem. So it is, you will have to maximize. So to get norm y star, okay, so let's y be in Rn. Now I want to think of it as a linear functional. It's how is it a linear functional? That is given by this formula, right? So I have to take maximum of the linear functional value. That means summation xi yi I equals 1 to n subject to okay. So what does that come out to be?
And since we are taking inner products, might as well take X, which is in the direction of Y.
Is that true? Is it always correct? Is that the best thing to do?
I mean, only
That's
then
why
can your inner product be
better not call
maximized,
it
right?
inner product. Better not call it inner product, because so I'll tell you a case where it is so if P is 1, okay, so then and let's take, so you're trying to maximize x1 y1 plus up to, let's just xn yn absolute value subject to absolute x1 plus up to absolute xn less than equal to 1. Okay, y is fixed. I give you a y. So how do you maximize this subject to the sum of this mod xi is less than equal to 1? Okay. For simplicity, just remove all the absolute values. Think of all xi's and yi's as positive. Okay, you are given x1 plus up to xn has to be 1. You know it will be equal to 1. How do you maximize x1 y1 plus up to xn yn?
Set xi is equal to yi.
Is that a good idea? So here is a question. So I mean, so this is yeah. So what do I say?
Like divided by to make it equal to 1.
Say no. I
Like
mean,
normalized.
suppose I give you, you have 100 rupees. Okay. So there are some 3 fruits. Let's say apple, mango, orange. Apple costs 10 rupees, mango costs
Oh,
20 rupees, orange
right,
costs 50 rupees. You want to
right,
maximize the number of fruits you get. What will you do?
right. You just get the cheapest one. So like
Is
you
the
you just put everything in the biggest one.
You put all the, so it makes sense. So if y1 beats all the rest, it makes sense to take x1 equal to y1 and set the rest equal to 0. So if mod yk is max of, so there can be several of them. So I'll just write it like this. Suppose k is an index which attains maximum of yk, then just take xk equals 1 and xj equals 0 for all j not equal to k. That is what maximizes the sum. Okay. So then what does that lead to? Gives, in this case, summation xy yi absolute value will be just mod yk, which is, to give you the clue, it is the L infinity norm of y. So when p is 1, you get the infinity norm on the dual. Is that clear? So what your intuition was, that's why I said don't think of it as inner product. Summation xi yi, it's when both x and y are, when we are thinking, it's better to not call it inner product. X is in one space, y is in a different space, so to speak. That's better to keep it clear that way. You'll understand later when you get used to these LP spaces. So it's not that intuition you had made sense because you are thinking of Euclidean balls, but here the balls are not Euclidean. So the thing is, they are not, the balls are not round, right? So you might be able to go in a slightly different direction than y, but take something that is longer in Euclidean norm, so to speak. That is why that intuition doesn't work. Anyway, so this p equal to 1 case shows that doesn't work. So the answer, what should be the answer in general?
Should it be like 1 by q such that 1 by p plus 1 by q equals 1?
Right. So that is what should come. So let's, can we do it? I mean, so is it possible? I mean, can I'm asking myself whether I'm capable of doing maximum. So you can do calculus, blind calculus and do it, or is there some better way? So let's just see. Summation xi yi. Right. Yeah, how do you do this?
So how about the following? You take a look at the ball xp equals 1, and then on this ball try to identify the point with the maximum L2 norm, and then try to find a maxima among those points.
But then that maybe have no relationship to y. That may be sort of orthogonal to y, right? This, then you won't get anything. You want to maximize this quantity. So if you just pick the ones with the maximal norm, so what do the norms
Yeah,
look
that
like?
will
It
not
is a
help.
good idea to do it in R2. It is a good idea to draw these pictures in R2. So the unit ball, okay, so this is a very bad picture of the unit ball. So the in L2 norm, the unit ball is the one that we are familiar with when P is 2. But when P is 1, what is the unit ball? X plus y equal to 1. So it looks like this. So this point is 1, 0. This is 0, 1. And then symmetrically like this. Okay, this is the
Right. I see how this will not help.
when P is infinity, it is the maximum of the two. So it will be, this will be the unit ball. Again, it passes through 1, 0, 0, 1, but this is the unit ball. So so you can imagine that so the way when p you go from 1 to infinity, this thing sort of starts bulging like this. At some point it becomes the round ball, and then it goes on further bulging and becomes this square oriented in the other direction. That's how you should think. So other p balls, it's not easy to write down. You can write a formula. I mean, it's easy to plot it on a computer, but it's not so easy to write it down. But it interpolates nicely between this shape and that shape. passing through this. All of them are symmetric about the two axes. Okay, so let's do blind Lagrange multipliers. Okay, so how do you maximize? So one way to do is Lagrange multipliers. So what do? You take summation xi yi, introduce a Lagrange multiplier. Okay, there is an absolute value which makes it horrible to differentiate, but I will ignore that and just do it. You should always do it. Okay, so justification comes later. You should get the answer first and then worry about all that. So if you do it like this, how do you maximize this thingy? Actually, I mean, maybe I can get it from here actually. So there is another way to do it. So in proving Holder's inequality, I told you there is a very key inequality, which is this. Oops. Right? A power p by p plus b power q by q is greater than or equal to ab. I should be able to get it from there. For a moment, let me just erase this Lagrange multipliers and see. Can I get it from there? One thing I forgot to do, maybe this reminds me to do, but okay. So we know that xi to the p for each I have this inequality, right? Where q is okay. If you choose q such that this happens, then this we know. Now you add over I. You get LP norm of x to the power p over p plus LQ norm of q to the power q, because that 1 over q doesn't come, right? Summation xi to the p is the LP norm to the power p, and this is LQ norm to the power q over q greater than or equal to summation xi yi, I equals 1 up to n. So now if we force norm xp less than or equal to 1, then we get summation xi yi. Actually, I should have put all this. Okay, so all this was with positive. Okay, so I forgot. Yeah, I should put an absolute value on all this, because that was for positive numbers. So all this is with summation mod xi yi. Okay, now then, so this is, of course, this is greater than or equal to summation xi yi absolute value. So you get that summation xi yi, when norm xp is less than or equal to 1, you get that this is less than or equal to norm yq to the power q by q plus 1 over p. Right? Okay, something is off. I mean, I wanted. No, this doesn't directly give. Sorry. Yeah. Yeah. Something is a bit strange. Yeah, I should have got, yeah, so why this extra 1 by p? But okay, what it reminds me of though, I mean, is one thing that I forgot to say here, which is when the equality is attained in these inequalities. That is something actually quite important. I forgot to say that. So we'll come to that. But okay, so there is a yeah. So I'm now slightly confused. Why am I getting an extra? So the maximum it attains should be this. Okay, this is only an inequality. So how can I attain this? So I should, when does, okay, let's go back to this one. When do I attain equality here? If you remember this proof where I made this rectangle and showed you the area. So here, so let's work out all the equality cases in the inequalities. Okay, sorry about that. So I should have done that last time. I completely forgot. So equality, if and only if this
B is a to
rectangle
the
is right. So B is a to the power p minus 1, right? Is that clear? B is a to the power. So B, oh, sorry, no. Yeah, X is, sorry, B to the, Y is X to the P minus 1. So B should lie on that. B is a to the P minus 1 or equivalently. That's the same thing. A is B to the Q minus 1 is the same thing. That is when the equality is attained. Okay. So that is clear. That's when the equality is attained because that's when the rectangle is. So if we go back here in using the Holder inequality, here we got use that inequality fx to the p plus gx to the q blah blah blah, and then it goes through. So to get equality, you have to have equality everywhere, right? So for this to happen, when does equality happen? So if equality, when, sorry, what is that? Yeah. So maybe there is an even more symmetric way of writing it. So let me write. So B equal a power p minus 1, or A is B power q minus 1, or even better, if I raise this to the power, I think B power q is a power p, is it? Or so what is it? P 1 by p plus 1 by q is 1. So p minus 1 by p is equal to 1 by q. So q into p minus 1 equal to p. So okay, so let me raise this to the power q. Then I get to the power q. Right. If I raise this to the power q, I get b to the power q equals a to the power p. Okay, because p minus 1 into q is p. So b power q. So this looks, I mean, a more symmetric way of writing it. So going back here, so this equality holds when fx to the, so b is what goes with, b is like y and a is like.
It's 4 o'clock.
So this is fx to the p is fx to the p equal to gx to the q. Okay, so that is when, so this with equality. So let me just write here with equality, if and only if f to the p is equal to g to the q, but you don't need to have it everywhere, almost surely with respect to mu, because if it holds for almost all x, then the integration will not create a problem, right? So, but equality must hold. Otherwise, this inequality, if it is not holding almost everywhere, the integral will create a strict inequality by the positivity or monotonicity of integral. So this is the condition. So this is the right intuition. So this is what, when Shekhar said we should take x and y aligned, that's when I remembered that I didn't do this. When p is 2 and then q is also 2, that comes to the case where f equal to g, right? So f square equal to, when f and g are positive, f square equals g square is same as f equal to g. In that case, they have to be aligned. Otherwise, it is not f and g that are aligned, but f power p and g power q that are aligned. Okay, similarly, you can work out. So when does equality hold? So read up the equality case here. So going back here, that is what happens. So the thing is, so what I want to say here is that, so here you will get a multiple of the LQ now. Okay, I didn't, right. So I got this. So this equality holds when you take x. So here equality holds when xi power p is yi power q, or mod yi power q. So that's what you should do. You should take xi so that mod xi to the p is mod yi to the power q. So then you will get an equality in this situation, right? This becomes equality. But then you also want this to be equality. So you choose sign positive greater than equal to 0 for all I. So that this also becomes equality. So working that out, you see that the best thing is to pick. So best choice is xi such that xi yi greater than equal to 0. That means that is the sign of xi is the same as sign of yi. Okay. And mod xi to the power p is mod yi to the power q for all I less than equal to n. If we do that, what do we get? So then, in other words, so then summation xi yi absolute value is same as summation mod xi yi because it's all the same thing. They are positive. I mean, I don't even have to. Xi yi is positive, so this is just. I don't need to write the absolute value. Which is now I found what is xi, right? Basically, this is like yi to the power 1 by q. So this is mod yi to the 1 plus 1 plus q over p. Sorry, not 1 over p, but q over p. Now, what is 1 plus q over p? Yeah, something is a bit strange. If I pick okay. So yeah, maybe I made another mistake here. So right. And you can mistake. Yeah. So what is it giving me? It is giving y to the 1 plus q over p. Something is wrong there. What is it? Okay. This x is okay. So that is probably okay. But what is this p plus q over p? But the norm of x is not 1, right? So we have to take, you have to take xi. So summation xi to the power p to the 1 over p will become summation mod yi to the q to the power 1 over p. Right? So that is also clear. So now what is, but what is this? I mean, something is a bit fishy. I'm slightly confused. So we have to divide this by this, but this is coming out as 1 plus q over p. That doesn't make sense. I mean, I want that power outside. I want yi to the power q to come outside. Okay. So this is okay. 1 plus q over p is, if I pull out q, it is 1 by q plus 1 by p, which is q. Okay, so that was something that so this is same as summation yi to the power q. So if you take the ratio, you get summation yi to the power q whole to the power 1 minus 1 by p, which is same as summation yi to the power q to the power 1 by q, which is norm by q. Okay, maybe I lost some of you in going back and forth. The thing is, I should have done the equality case last time. Okay, so just take this point that equality holds in this inequality, in the key point inequality here, when a power p is equal to b power q. That goes back to the equality case of Holder's inequality and says that this happens if f power p is equal to g power q almost surely. Okay, that is fine. Now, coming to this case, so what I wanted to do was maximize this. So I just use that inequality. So here I have the inequality, but to maximize this side, subject to, if I want to maximize this side, well, I am going to fix this to be 1, but here I did it slightly differently. To get the best case, we will pick xi to the p to be equal to yi to the q. And then you get this, and you see that the norm you get is LQ norm. It's possible I fudged something, but is it okay overall? The calculations are something you can do yourself. Why I brought it up, actually, I spent more time than I wanted. So in general, if you have a norm which looks like, so this is how the duality comes, and this persists in LP spaces also. Okay, in the infinite dimensional setting also, this type of thing is true, but with caveats, because now the space itself changes. In the thing about finite set is that all the LP spaces, the underlying vector space is Rn. But when you go to an infinite dimensional vector space, you go to, let's say, R, real line, and you look at LP of R, the vector spaces themselves are different. What functions are square integrable are not the same as what functions are integrable. And what functions are integrable to the power 3. They are all different spaces. The spaces also change and the norms also change. One has to be, that is the one thing one has to be cautious about. But also the proof is also not, formally speaking, you can push this, but you have to write a more proper proof for that. But the reason I brought this up is it is a simplest setting in which you see the duality of LP and LQ. And also it may be something that some of you have seen. That's why I brought it up. So what is it? So in general, if X is Rn and we have a norm, which is norm X equal to, let's call it phi X. So then it is easy to see that. So phi of alpha X must be mod alpha phi X, right? That is, that's the homogeneity, but also phi of, you can see that phi of X plus Y by 2 equals 1/2 of, so this is less than equal to phi of X by 2 plus phi of Y by 2, which is 1/2 of phi X plus phi Y. So what it means is that phi is convex. If you know what a convex function is, and you should, so this is a convex function. So what will be the dual? So X star will be again Rn, but what is the norm star? Will be some psi of Y. So what is that psi of Y? You can write it as max over X of xi minus phi X. Something like this is what you get. I'm just writing this so you can work it out. This is just something I'm saying on the side, by the way. You can ignore it also if you're not interested. You get this, and you may have seen this kind of thing. This is what is called convex dual. So convex dual. So if you have a convex function phi, you can generate a new convex function psi by this formula. It is also called Legendre dual. So you see it all the time in mathematics. It's a very, very important transformation. From one convex function, you get another convex function. It is called a dual because if you apply the same formula to psi, you get back phi. Okay, so that's not obvious. I'm just mentioning this. So if you have seen any course in convex, this convex optimization and so on, you would have done much of this. Unfortunately, the syllabus of mathematics is such that although you do a lot of analysis, convexity is kind of hidden in some place. You don't do much, but this is a very, very important transformation called convex dual. And what is behind this? All this is actually convexity, the norms. So when you have a norm on Rn, the dual norm is exactly the convex dual. Is given by the convex dual, and the way it works is the convex dual of the function. If x power p, a power p by p is a convex function, its convex dual is b power q by q. That's how things work. So when you put LP norm here, you get the LQ norm on the other side, maybe with some scalar constant. Okay, so that is maybe depends on the way you normalize, but So it may be not LQ norm, but 5 times LQ norm, which is okay. But that is how the relationship comes. So this is something to just know. Okay, for those who are interested to read further, you can do it. But what I wanted to convey was this point about the relationship between P and Q, the dual norms that you already see even in finite dimensional vector spaces. Okay. So the corresponding theorem in infinite dimensions, I may or may not be able to do. I mean, it takes some time, so I'll probably skip it. But I will write the theorem later. Okay. Any questions, comments so far? Okay. If not, let me go to something else. I mean, it is actually not something else. It is something of a similar nature, but it may not look like that. So I'll not try to make the link right away with what we were saying just now. This is Riesz representation theorem, amazing theorem. So let me write the theorem and then discuss it. Okay, so this is the theorem. X. So let's suppose X is a locally compact Hausdorff space. So if you don't know what that is, you can take X to be Rn or 0, 1 to the n or some compact subset of Rn, etc. Okay, so you can take many things. So you just, if you do not know what locally compact Hausdorff space means, the statement is, okay, Hausdorff space I won't define. You can think of a metric space where every point has a neighborhood. There's an open ball which is compact. Okay. So there are spaces where this is not true, that open balls, even if you take very small radius open ball, its closure is not compact. So locally compact Hausdorff space is, if you take metric spaces, it means that open balls of at least some small enough radius are compact. Okay, or when you close them, that becomes compact. So okay, but you don't, if you don't know, you lose nothing in this discussion by sticking to Rn and 0, 1 to the n. Okay, so you get everything there. There is no problem. Okay, just think of that case. But I will state the theorem in generality. So then Cc of x is the space of all compactly supported continuous functions on x. So what that means is it is all f from x to r such that the set where f is not equal to 0 the set where f is not 0 is contained in a compact set. Okay, so for example, if x is r, so a function like this which becomes 0 outside some bounded set, that is what I mean, it should be continuous everywhere. Okay, even it should be continuous everywhere and it should vanish outside a bounded set. After some point, it is on both sides, it is 0. Such a thing is compactly supported continuous function. Okay, support is the set of x where f is not 0. Okay, or the closure of that is often called the support. So often f not equal to 0, this closure of this set is called the support. Okay, so that should be compact. So that's how in R2 also the picture is the same. Outside some bounded region, it should vanish and it should be continuous everywhere. That's what Cc of x is. Now the thing is, what is the Riesz representation theorem telling us? So Riesz representation, okay, let's define more things. So L from Cc of x to R linear, that means it's a linear functional. Okay, so L of alpha f plus beta g. You take two functions, alpha f, so linear. So let's remove this bracket, it looks confusing. So if I take two functions f and g, so L of alpha f plus beta g will be alpha L of f plus beta L of g. So alpha beta f and g in CC of x and alpha beta as scalars. So linear, and I have one more assumption that it is positive. What it means is that if f is a non-negative function, if f in CC of x and f is greater than or equal to 0 everywhere, it's a continuous function, so it should not be negative anywhere. Then this is pointwise. Then L of f should be non-negative. Okay, that's what it means to say this is a linear positive linear functional. So we say L is a positive linear functional. So it's called a positive linear functional if it has these two properties. Okay. So do we have any examples of such things? So do we have, can you give me an example? So even let's now stick to the case when x is r. Okay. So can you give me an example of a positive linear functional on CC of r? So can you give me any example?
Integration with respect to limit measure.
Okay, so one example, L of f equal to integral over r f d lambda. So this is, you can define any compactly supported continuous function is firstly measurable and it is integrable, right? Because it vanishes outside, it's bounded and it vanishes outside a bounded set. So the whole thing is integrable, is clear. So you can define this integration, and that is a positive linear functional. Even in fact, if you don't like this, you can even think this is same as even Riemann integral. You don't even need to know Lebesgue integration to define this. You can take the Riemann integral of a continuous compactly supported function, and that is linear, is clear, and it's positive because f is non-negative, then the integral will be non-negative, right? So we can do that. Okay, any other? Can you give me any other example?
L of f equal to f of 0.
Okay, L2 of f equal to f of 0. See, that is it linear? Because if I take alpha f plus beta g, the value at 0 will be alpha f of 0 plus beta lg of 0. And if f is non-negative everywhere, then certainly at 0 it's non-negative. So this is also okay, right? So you can take such things. Two f of 0 plus 0.1 f of 1, for example. So that such things. So right. So these are examples of positive linear functions. So but you notice that these are actually integrals with respect to some measure. This is f d mu, where mu is delta 0. The degenerate measure at 0, if you take that, integration with respect to the degenerate measure is just the evaluation at that point, right? And what is this? This is integral f d mu, where mu is 2 delta 0 plus 0.1 delta 1. You take a measure which puts mass 2 at 0 and 0.1 at 1. Integration with respect to that will give you this. So these are all integrals with respect to some measure on this R. And that's what Riesz representation theorem says. Is this clear? That are these examples clear? That these are like this? So what Riesz representation theorem tells is, so this is, by the way, there are two people called Riesz, they were brothers, and to make things confusing for everyone, They both worked in the same area of functional analysis. The more famous one is F-Riesz. There are a lot of theorems in functional analysis which are due to F-Riesz. So this is it's a Hungarian name. I don't know exactly how to pronounce, Riesz or something. So they are Hungarian. So the other one is M. What is M actually? This is Marcel Riesz. Yeah. So yeah, to make even things confusing, if you go to an advanced class, there is a theorem of F and M Riesz. So so they put some theorems together also, but this is due to F-Riesz. What he showed is that if X is locally compact Hausdorff space, okay, and L is a positive linear functional, on CC of X, then there exists a unique regular Boyle measure. Okay, I will recall the definition I had at some point defined. Regular Boyle measure mu on X and its Boyle sigma algebra. It has a topology, so it has a Boyle sigma algebra such that L of F is nothing but integral with respect to mu for all F in CC of X. Okay. By the way, the converse part is kind of clear. That's why I have not written it into the theorem. So that I could have written it as the following or equivalent and made two statements. Statement one is L is a positive linear functional. Statement two is L is represented by integration with respect to mu. But I just wrote the non-trivial part. Note, converse is easy. If mu is a measure on X, Bx, such that is radon. I'm just introducing words to just so that you know it. Radon means mu of k is finite for all compact k. So a measure that gives finite measure to compact sets. So for example, if you take real line and take counting measure on rational numbers, that is not a radon measure because the measure of 0, 1 will be infinity. There are infinitely many rationals there. So that will not be a radon measure. Radon measures are ones. The whole measure can be infinity, but any compact set should have finite measure. So then defining integral with respect to that defines a positive linear functional on CC of X. So from a measure to get the linear functional is easy. The reason I assumed radon is otherwise this may not be well defined, right? This F has to be integrable with respect to mu. Compactly supported continuous function. Okay. So if F is supported inside a compact set K, then it's also bounded on that set K by, let's say, 10. Then you know that the total mod, this will be integrable because the measure is finite and the bound is there. So it will be integrable. So that is easy. So that's why you need to assume radon. Otherwise, you may not be able to integrate compactly supported continuous functions. So, but if it's radon, it's obvious that the compactly supported continuous functions are integrable. So this is well defined. And it is a linear functional is then clear because linearity of and positivity are precisely the points that I emphasized about the integral. Okay. So all this you can think, I'm going on writing with X, but if you are not comfortable, think of real line or Rn in general. That is enough actually. So such a situation, these are but the converse is what is being said, that what is integration? Integration is nothing but a linear positive functional. So the points, the properties of integral that I was emphasizing, linearity and positivity, that's all there is to integral. Anything that is linear and positive on Cc of x is actually integration with respect to a measure. Any questions about the statement? Is it clear? This is a great theorem. This is a wonderful theorem. Okay, so I want to make some remarks before going into the proof. I mean, I want to discuss the proof, maybe not full line by line proof, but essentially I'll indicate for you the proof of this theorem. But I will, what I want to discuss is, so actually this theorem also has some interesting implications, maybe philosophical implication if you want. So another remark. See, when we, but before that, are there any questions? Is it being clear? I mean, so all I'm saying is all positive linear functionals on Cc of x. You take x to be Rn. So Cc of Rn, the compactly supported continuous functions on Rn, if you have a positive linear functional, it is integration with respect to a regular Borel measure. Okay. I said I would recall what is regular. So this one, so there are 2 points, right? So you may remember, so oops. So this has 2 things. So outer regularity says that mu of A is infimum mu of G. G contains A and G is open. And inner regularity says that mu of A, so this is for all A in the Borel sigma algebra. So similarly, for all A in the Borel sigma algebra, you can write it as supremum of measures of compact sets contained inside A. Okay, so for all A in B of the Borel sigma algebra. This is what outer and inner regularity are. If a measure has this property, it is called regular Borel measure. Okay, this is somehow a technical condition that is required, without which uniqueness fails. You may have a non-regular measure giving the same integrals as a regular measure apparently. So I don't have an example in mind. I have seen it at some point. I don't remember. But so this is a technical condition which is required, and indeed measures that are not regular are, why do you want to spend your life with them? Okay, so you can find nice measures with which to spend your life with. So that's all. So that is the point. Okay, so now I want to come to this philosophical remark I was saying. See, long ago, very long ago, when we defined measures. So what was measures? So when we defined measures, okay, maybe there is nothing to write here, so I'll just speak. So when we define measures, you remember what is measure? I mean, at first we started with volume. So let's stay with Rn itself. We were interested in understanding the notion of volumes and extending it to as much as possible, right? Volumes of sets. So what we had in mind was that volume should have certain properties, okay? So one thing is clear, if A and B are disjoint, then volume of A union B should be volume A plus volume B. Later we realized that even this is too much to ask if you want to assign volume to all sets. So we decided that we will not assign volumes to all sets, but we will stick to a smaller class of sets. But we certainly want this property that for a disjoint union of 2 sets, volume of the union should be the sum of volumes. But that's not all we did. We in fact asked for a stronger condition, countable additivity. We asked for volume of a countable union of pairwise disjoint sets to be the sum of the volumes. Now, at that point, I mentioned to you that I don't have any justification to give you, and I didn't give any justification. We just said, why did we ask for? So the countable additivity of measure. Why did we ask for countable additivity of measures? Okay, so I'm not worried about the fact that measure space is x, f, mu. So this sigma algebra is not the whole set that we have discussed extensively, that it is too much to ask f to be the whole of the power set, that then we will be unable to define volumes properly. That is okay. So I'm not worried about this sigma algebra part, but why should mu be countably additive? Why not finitely additive? So the emphasis here is on countable. So finite is something we can accept. Okay. Acceptable means it is something that we will agree. We can agree that we should ask for finite additivity. I mean, volumes, that's what should satisfy. So this problem, we just said that, okay, you take it on faith that this is how it works. In fact, in the beginning, it was not clear to people whether countable additivity is the right framework. You know, when a theory is being built, many things are done. Everything is in a fluid situation. Nobody is clear about all the things. So it is not clear what is the right definition, what is the right setting, and so on. So especially in probability, there were many people who were many strong people, many top probabilists who are not fully convinced that countable additivity is something we should ask for. So many people work with finite additivity, but slowly over the years, it is clear that you can do both. I mean, it's a definition. You can impose finite additivity, you can impose countable additivity. So the theory with countable additivity turned out to be much richer than the theory with finite additivity. So everyone accepts countable additivity now, though there may be some esoteric situations where you should consider finitely additive measures. That may happen, but keep that on the side in mind. But what I want to tell now is that Riesz representation theorem, in some sense, gives you a justification for countable additivity. How does it give a justification? Look at the question. Okay, forget the conclusion. Forget the conclusion part. Okay, so let's look at locally compact Hausdorff space. You think of Rn and positive linear functions on CC of x. Positive linear means linear transform, linear like this and positive. See, this looks like a reasonably natural enough question. Okay, so what are possible linear positive linear functionals on CC of R? You can ask that question. And notice that the question has no countability built into it, right? This is about L of alpha f plus beta g. So this is a finite additivity type thing. And positivity is something completely different looking. So there is no countability apparently built into this question. But what is the conclusion? The conclusion is that there exists a unique Boyle measure. What is measure? Measure means countably additive measure. So without putting countability into the question, the answer spits out countable additivity. So in some sense, if you are a person who was adhering to finite additivity, you would not have a Riesz representation theorem. So this itself, this question, which, okay, whether you accept it's a natural question or not, I leave to you. But this has no countability built into it, but the answer has countable additivity. It says that all such positive linear functionals are represented by countably additive measures on the Boyle sigma algebra. So in that sense, the Riesz representation theorem gives a sort of justification for countable additivity. That's a remark I wanted to just leave you with. Okay, any questions here? Okay, so then I want to give you a sketch of proof. Just give me a moment. Okay, so if there are no questions, what I want to do is give you a sketch of proof. I have 25 minutes. I think I'll be able to give a sort of sketch. Okay. Yeah. Okay, so no questions. Okay, so let's go towards the proof. Actually, the proof is something. I was looking for what is the simplest proof I can give you. So the locally compact Hausdorff space, there are proofs given in many books. I mean, many books actually. For example, Rudin's real and complex analysis. He does in fact in the opposite way. In a way, he first develops Riesz representation theorem and then brings out Lebesgue measure. Lebesgue measure is defined as, he starts with Riemann integral that gives you a positive linear functional. He proves Riesz representation theorem and then consequently there exists a measure. That's how he proves existence of Lebesgue measure. Instead of doing all the things we did to construct Lebesgue measure, he does it this way. But proof of Riesz representation theorem is not that short or easy if you have looked at Rudin's real and complex analysis. It's also given in many other books. So there is one book I have referred to in, it's a succinct book. It's nicely written. I have never heard of this book referred to by others, but I found it somewhere and I liked it, by Kohn, C-O-H-N. It's just, it's a rather short book and everything is done nicely there. So there also you find a proof of, and many books have a proof of Riesz representation theorem. Bogachev's book has all those. But something that occurred to me, this must have been there in older books. But now that just yesterday when I was thinking about it, it occurred to me that the whole thing is actually something parallel to what we have done. So what I want to indicate to you is the parallel to what we have already done. Now, this may not lead to a complete proof. I have not yet written down all the details. Okay. So that's why it may be that it is not a complete proof. Maybe there are problems. But if so, then I don't think so. It is probably fine. It's probably fine. But let me indicate what is the point here. Okay, so let's not worry about the very general situation. Let's first start with, so X is R and L of F is integral Fx dx on R. Okay, so this is, if you want, it is the Riemann integral. What this should give, should lead to L is integration with respect to Lebesgue measure. This is already there. Okay, so that's what Riesz representation theorem leads. But how? So that is the question. So suppose we did not know Lebesgue measure and I start with this positive linear functional. Can I get the Lebesgue measure by this? Okay, so this is what I was thinking. I was worrying what is the best way to present it. Then, so what would be the best way? See, how do you know to construct measures, right? So we have to construct a measure. So in this case, it should turn out to be Lebesgue measure. But in general, it will be other measures, but doesn't matter. Let's stick to this case to understand. I'm just first giving a motivation for the proof. So what should you do? How would you construct measures? The only way we know is to construct an outer measure and then get the measure, right? So one way to construct, so how to get a measure from L. Okay, so we know only one way. Construct an outer measure and blah blah blah. Okay, then you restrict to the sets which satisfy the Carathéodory condition. That gives you a measure, and you see how big that sigma algebra of measurable sets is, etc. Okay, so that is what. So the question is from L. So now the question becomes how to construct an outer measure from L. Okay, how do I construct an outer measure from L? Okay, so what do you do? So here I want the, see, I have integrals of, what we did earlier is we had lengths of intervals, right? Then from there we went to lengths of measures of general set. So here outer measure. So here how one obvious way, one natural attempt. Let me put that. How would I define? So I will give it the name mu hash of A for any subset of R. You define the outer measure of that to be the infimum of L of F, where over all F which is in CC of R and F is greater than or equal to the indicator of A. Right, see, if ultimately you are going to show it is integral with respect to something, so let's say A is an interval like this. See, if ultimately you are going to show L is integral with respect to some measure, then if f is greater than equal to 1a, integral of f should be greater than equal to integral of 1a with respect to that measure. But integral of f with respect to that would be LF, and integral of 1a would be mu of that, measure of that. So certainly all these numbers should lie above the measure of that set. Okay. Of course, we are now defining for all subsets. We'll have to restrict to that class. But this clearly that these numbers should beat that. So what I want to do here, the idea is that you take all compactly supported continuous functions, which are, if this is my set A, the set A is, let's say, this interval, then what does f greater than equal to indicator A mean? It means that the function is at least 1 on this interval. So there's no point taking much larger. So let's say it has to take the value at least 1 here. Maybe you can make it larger if you want. It will only make L of f larger. We are trying to minimize the value of LF, so to speak. So you would take something like this, but you can't simply drop it off because it has to be continuous. So maybe we will take continuous functions which look like this, compactly supported continuous functions, which kind of drop off steeply. And maybe we take the infimum of L of f of all such functions. Okay. So that could be one possible way in which you approximate, but the general definition would be this. So will this give me what I want? So question is, will this give me an outer measure which I can complete to a which then I can restrict using characteristic cut condition to a measure? Okay. Any remarks? What do you think? Will this work? Will this not work?
I guess when you take an unbounded interval, there will be some problem.
Okay, that may be a problem. That may be a problem, but okay, at least for this particular one, unbounded ones would get infinity. We agree. So you are right. So this works. This doesn't always work because this set may be empty. That is the problem, right? So this is a problem that this set can be empty. Okay, so maybe since I am only talking about motivational thing, so let me. It's a good point. So what Bappa is saying is that this set may be empty. So then what infimum am I talking about, right? It may not work. So let's take X is a compact set. 0, 1. Okay, in this case, there is no problem. There is always, so let's, instead of CC of R, yeah, so now I'll just write X. X is actually 0, 1. So now your objection disappears. Is that okay? So this should be on 0, 1. So this should give only Lebesgue measure on 0, 1, but everything is happening in 0, 1. So let's say this is 0, this is 1. So now compactly supported is a trivial condition, meaning all continuous functions are what we are looking at. In a compact space, all continuous functions are compactly supported. There is no problem if X is itself compact. So then this collection is always non-empty because f equal to 1 is in the collection. So this is always a non-empty infimum. So then it is well defined. Okay. Still, would you say that this gives you a good outer measure or not? So
Take A to be a countable tensor subset.
Okay. So then if you look at, so one problem, if you take A to be, let's say, Q intersection 0, 1, and F is a continuous function on 0, 1, F greater than equal to indicator A, that implies actually F is 1, right? Because if it has to be greater than equal to 1 on rationals and it's continuous, it has to be 1. So this mu hash of A is actually 1. So it's not the Lebesgue measure of Q. Does this remind you of anything?
Jordan measure.
Exactly. This is the Jordan measure. So in fact, so I can leave it as if you want. In fact, this is actually the exact same problem we had with Jordan measurable sets, right? in the Jordan measurable sets, what we were, so let me write down the thing, you may collect then. So in fact, I can leave it as exercise that show that mu hash is lambda hash. What was lambda hash? You may recall lambda hash of a set A, or I have it somewhere here, right? So long ago, Jordan measurable sets. So what was lambda hash of A? Lambda hash of A was defined as the infimum of the sum of lengths. You take any finite cover of A by intervals. Okay, you take any finite cover of A by intervals. I have written them disjoint, but you can, if they were not disjoint, you can always disjointify them. It's only finitely many intervals. So, and for each cover like that by finitely many intervals, we take the sum of lengths and then we take infimum over all such covers. What I'm saying is this is exactly what you get by taking this mu hash. Mu hash is the, okay. So you can look back at this. So what you get here is that Jordan measure, which is not what we wanted. So how did we fix the problem? Okay, so this doesn't work. So what should we do? How did we fix it last time? So lambda hash was not good. We did not like that. So we went to something else. What did we go to? We went to lambda star, which was lambda star outer measure was
Countable instead of finite.
Yeah. So let's why not? If something works once, you try it again, right? So maybe we try exactly similar things. Okay. By the way, to make the analogy clear, if you want, this can also be written if you want in a complicated way as infimum of L of F1 plus up to L of Fn, where n greater than equal to 1, Fi or NCC of R of X, and summation Fi greater than equal to 1. So it's just a complicated way of writing because that this is just L of F1 plus up to Fn. If Fi's are compactly supported continuous functions, so is F1 plus up to Fn. So this and this are the same thing, but this is just to make it look very much like the Jordan thing, right? So here this was infimum of L of F, but you can write it just as well like this, where summation Fi beats indicator. This is like saying A is covered by the intervals. So this is the analogy. So what would be the right modification? So in analogy with going from lambda hash to lambda star, let us define mu star using countably many functions. So that is, we define mu star of a set A as the infimum of summation L of Fi I equals 1 through infinity, where Fi are in CC of X. So I'm still taking X to be 0, 1, Fi are in CC of X, and summation Fi beats the indicator of the set. Is this okay? So we can define mu star of A like this. This, at least, I mean, I haven't seen this in a book. I have to look. It will be, I'm 100% sure it's written in some book like this, but I don't know. This is something I just worked out yesterday and today, but I somehow had not looked at it this way. Usually in books, you will find a much more slick proof. Okay. You don't do this, you do something else, but it is less natural looking. Whereas given what we have already done, this seems to me more natural, or maybe it is simply because I thought of it now. But so I think the ideas are okay. If not, anyway, you can read up the proofs in the books. But let me try telling this, even if it is not entirely correct and if there is some place I get stuck at. Okay, so we try to define like this. The claim is that this mu star, so maybe now I can go to a sort of more general situation and define like this. Okay, so let's work with at least compact situation. So definitely, maybe I go to a New page. Proof of Riesz representation when X is a compact metric space. So I just go a bit more general, that's all. Instead of if what I'm thinking is not wrong, I will get a proof for compact metric space, and that is good enough. I mean, locally compact, you can do it afterwards. But what I want to give is the basic idea. Okay, so you should understand the basic idea. So then the various technical details will have to be filled in. So let's take X to be compact metric space with metric D. So the only example you want to take is you can take 0, 1 to the D, I mean, or 0, 1 to the N. So you can take a product of closed intervals, that is fine. Okay, so then, and L is, now I don't have to write C of X, C of X to R. Positive linear functional. Okay, and then we define mu star of A equal to the infimum. I am repeating the definition. L of Fi, I equals 1 up to infinity over Fi in C of X such that summation Fi beats indicator of A. Okay, suppose we do this. So claim 1, I want to say this is an outer measure. Okay. So by the way, this is for all subsets. And so since by the way, this is so this is always bounded by L of 1. Okay, so because 1, the constant function 1 is a possible way to cover this. So you can take F1 to be 1 and all the other Fy's to be 0. So then you will get something. So L of the constant function 1 is an upper bound for mu star of A. Okay, so let's prove this actually. So let's prove this claim. So that's the reason I stick to compact. So this is the problem that, so since is a valid cover, so I just call it cover, the set is non-empty. When you write infimum supremum, one has to worry first that the set you're taking is non-empty, otherwise it may not make sense. Okay, so now what is outer measure? What are the properties of outer measure? So first of all, clearly, L of the constant function 1. Okay, so that is one point. That's not related to, I mean, I don't need it, but I just wrote it here. So what do I need for outer measure? What are the properties of outer measure? One is monotonicity. If A is contained in B, then let's say A contained in B implies So if A is contained in B, mu star of A is less than or equal to mu star of B. So this is actually obvious. Because if F is greater than or equal to indicator of P, or so if summation Fi is greater than or equal to indicator of B, then summation Fi is greater than or equal to indicator A, right? I mean, the infimum is over for A, the infimum is over a larger collection of this countable families of functions. Therefore, it is the infimum is over a larger set, so the infimum value will be smaller. So this is easy. It is the countable, and the other property is countable subadditivity. So what is countable subadditivity? So let A and B subsets of X and A be the union of AX. Okay. So want to show mu star of A is bounded by sum of mu star of A. Okay. So for each AN, find Fn1, Fn2, and so on in C of X such that just give me a moment, 1 second, I'll mute my. Hello. Sorry. So I went for something to attend to something. So let me come back. So yeah, for ANs we find this function such that this sum, since the infimum is that and it's always finite, so it is. So we find this Fnj so that this is less than mu star of AN plus epsilon over 2 to the n. Okay, so we do that. So then it's 5 o'clock. Such that, okay, of course, also summation Fnj over j is greater than equal to indicator A, I want. So then, if you take all n and j, Fnj, that is greater than equal to indicator A. And because that is the A is the union of ANs, this is true because the sum of indicators is greater than equal to indicator of the union, right? Because there can be overlaps. And also summation L of F and J over N and J beats is less than this one, summation mu star of AN plus an epsilon. I add up this epsilon over 2 to the n's. So this shows mu star of A is the infimum of L of such things. This is still a countable family. I have written it as a double array, but that's a countable family. So this shows that this is less than equal to summation mu star of AN plus epsilon, and for all epsilon. So hence we get the countable identity. So that finishes the proof that mu star is an outer measure. Okay, so the question is, then we always get a measure from the outer measure. But one other thing that I need to do is I need to know that when I do that, I get the Boyle sigma algebra. So what condition is there which guarantees that? Do you remember? I will do it next time, but let me just end with that point. So do you know what else I need to do now? Once I have an outer measure, I certainly get a measure on this sigma algebra of sets which satisfy the character condition. You may not remember all the details, But do you remember a nice condition under which you get a measure on the Borel sigma algebra? So this sigma algebra that we get should contain the Borel sigma algebra. What ensures that?
If the compact supports the satisfies the cathode cut condition.
Yeah, that is the cathode cut condition is one way to it, but is something simpler.
We had this lemma, right? A couple of properties that we had to check that we could use to straight away say that a certain outer measure extends to a measure.
Outer measure always gets a measure, not extends to it, restricts to a measure on the set of collection of sets satisfying the cathode cut condition. But maybe you are talking about this extension theorem where if you have a countable additive measure on an algebra, it extends to the sigma algebra. So then the compact, there is something that makes it easier to check the countable additivity on the algebra. But there is one more condition which makes it easy to check this. So what is that? To remember the metric property of an outer measure. So if two sets are separated in distance, then mu star of A union B is mu star A plus mu star B. Okay, I'll come back to that next time. So you can look back. There was a metric condition on measures. If I don't know where I had it. Oh, no, this is. Oh, sorry, here. Metric outer measures. Okay. Yeah, metric outer measures. Yeah, so this is a condition. If XD is a metric space and you have this condition, mu star of A union B is mu star A plus mu star B, when A and B are not merely disjoint, but they have a positive distance, then this cathode sigma algebra may be bigger, but it will be larger than the Borel sigma algebra. And I am happy enough to restrict to the Borel sigma algebra. So this is a condition I would like to check. That for the outer measure that I have now. Okay, I'll postpone that to next time.
Sir, here do you have assumed it to be, I mean, X to be a metric space or any topological space?
That's proof of Riesz representation when X is a compact metric space. Okay. So yeah, so that makes some things a bit simpler, right? But the general proof is, I mean, I think, but this is quite illustrative, and that's okay. We can leave it at that. You can look at the full details in the books. What happens if you don't have any metric structure, etc.
Okay.
Any other questions, comments?
Sir, in the Riesz representation theorem, in remarks, you told that we got the idea of countable additivity. So, from the theorem, from the statement of the theorem, how we got that idea? That is not clear to me.
No, the statement, the conditions of the theorem do not have countability in it. Conditions of the theorem is that X is a locally compact Hausdorff space and L is a positive linear functional on the space of compactly supported continuous functions on X. Okay, is there anything countable about it? Well, X is locally compact Hausdorff space is fine, CC of X is fine, they are just defined. Positive linear functional, the conditions are here. Linearity is a finite condition, finite additivity condition. There is no countable additivity condition here. Okay. And positivity, of course, doesn't seem to have any countability. So the entire conditions here don't have any countability in them. But the conclusion has countability in them. In that, this L is represented by a measure. Measure means it's countably additive. So without putting countability in, we have got countability out. So that way, it is naturally bringing out the importance of countability. That's what I meant.
Yeah, okay, so thank you. I got that, you know. Yeah.
Any other questions? Okay, if not, let me stop the recording. I think I have forgotten to put some of the recordings up, maybe one previous class, I will do that.